One, today we'll be discussing details in substitution reaction. There are several details that are involved in general substitution reactions. We have already studied alkyl halides, the nature of alkyl halides, nucleophiles, strong nucleophiles, weak nucleophiles, good living group, and non-living groups are also discussed in substitution reaction in previous lectures. Today, in this video, I'm going to give you a brief and details of substitution reactions as it involves their mechanism. So, for example, solvents are very important in substitution reactions, and these solvents could be classified as polar. Most of the substitution reactions, almost all of them, need polar solvents. So when we say polar solvents, we have also two types of polar solvents. One are protic solvents, the other is aprotic. When we say protic solvents, we mean that the solvent would contain some hydrogen that's attached to an electronegative atom. That means it could be an ionizable, or it's capable of making hydrogen bonding. Aprotic is polar solvents, but they don't have any hydrogen that is capable of doing hydrogen bonding. But the detail will be in the video. The next is mechanism of SN1 and SN2. The substitution reaction is classified into two broad mechanisms. One is a nucleophilic substitution, a unimolecular type when it comes to its mechanism, and there is a substitution reaction. It is a bimolecular, or SN2. So the details are in the video, so that's what we'll outline or discuss in detail these concepts. Third thing that would be discussed in this video is energy diagrams. So you have energy diagram for SN1 and for SN2, which are distinct mechanisms. Therefore, you would have two different energy diagrams. And also, we'll be discussing rate of reaction. Both SN1 and SN2 have different rate laws, where the rate of reaction for SN1 is written as rate equals K times the alkyl halide. Just that's the rate law for SN1. But rate law for SN2 is alkyl halide. Concentration of the alkyl halide is necessary, and also the concentration of N-nucleophile. That's why this is a bimolecular, this is a unimolecular mechanism. So I just want to remind you that this is an important part of organic chemistry, and most students find it a little confusing, but once you know all the factors that are important in substitution reaction, the solvent, protic, aprotic, the mechanism SN1, SN2, the energy diagram unique to SN1, SN2, and the rate laws. Once you understand all this concept in this video, you'll have no problem understanding substitution reaction, and you could answer any questions that's related to substitution reaction by just going through and studying what would be described in the next. Welcome back. Let's continue our discussion on nucleophilic substitution. In this section, we'll be discussing the effect of solvents in the reactivity of a substitution reaction, especially nucleophilic substitution. As you know, the nucleophilic substitution require polar solvents. Mostly the reactions are carried out in polar solvents. So even within polar solvents, you'll find that there are protic and aprotic solvents. When we say protic solvents, we mean that the solvents have a hydrogen bonding kind of solvent. For example, here you see water, here is methanol, these are alcohols, this is acetic acid. So the most important aspect of protic solvents is that they can solvate the nucleophile, meaning that if you have a nucleophile like fluoride, in this case as a nucleophile, it's a strong base because it's produced from a weak acid as compared to iodide, which is produced from a very strong acid. This is the acid form. So if you just study these two nucleophiles and study that the effect of solvent toward this fluoride and iodide, these are all protic solvents that can solvate the anion. So the nucleophile, in case of protic solvents, due to hydrogen bonding, would be solvated by the solvent. That means the more the anion would make hydrogen bonding with one of these solvents, the lesser it would be nucleophilic. Despite this being a stronger base than iodide, remember this because it's generated from a weak acid. So in most cases, stronger bases are strong nucleophiles. But if you remember what I just mentioned, these solvents have a tendency to hydrogen bond with the nucleophile. Remember, protic solvents would solvate the fluoride. That means, for example, if you take water, a hydrogen bonding molecule, one of the solvents, a protic solvent, because it has hydrogen that can hydrogen bond with a nucleophile, so the nucleophile would be solvating the fluoride anion through hydrogen bonding. So that means if you have another water molecule like this also hydrogen bond with the fluoride. That means the fluoride is not available as a nucleophile. So the nucleophilicity of a fluoride anion, even though it's a stronger base, is diminished by the possibility of hydrogen bonding by polar aprotic solvent. So clearly you can see the effect of solvents on the nucleophilicity of your nucleophile. So fluoride in this case, now fluoride is weak nucleophile in polar aprotic solvent. So the nature of the solvent, the reaction is being carried out, would affect the nucleophilicity of your nucleophile. In this case now, iodine is very large in size, so the solvation is not as strong as the fluoride. Fluoride is smaller. The iodide is less solvated, and it's also making less hydrogen bonding. That means it becomes a stronger nucleophile. It becomes a stronger nucleophile. This is just based on what solvent the reaction is being carried out. So it's very important for you to understand the effect of solvents during a reaction. You have alkyl halide, you have a nucleophile, but in addition to that, the reaction is obviously carried out in some type of solvent. So all of these solvents are protic. That means they have hydrogens that can be hydrogen the nucleophile. The more hydrogen bonding they make with any given nucleophile, the lesser that nucleophile towards a substitution reaction. So they diminish nucleophilicity. In addition to that, you have, I just mentioned water, methanol, ethanol, tert-butanol. This is acetic acid. Now let's see aprotic but polar solvents. So this group of solvents are called aprotic, meaning that they don't have a hydrogen that is capable of making hydrogen bonding. If you just look at the structure, this is the carbon-oxygen bond is the polar bond. It doesn't have any hydrogen that's on an electronegative atom. Therefore, they cannot make hydrogen bonding. They don't have protons on them. Here you have acetonitrile, you have DMSO. DMSO is a dimethyl sulfoxide. Here you have tetrahydrofuran, it's an ether function. You have hexamethylphosphoramide. It is also a aprotic solvent. No hydrogen bonding. No. Here is the aprotic solvents. So that's how they diminish the nucleophilicity. Here there is no hydrogen bonding. So these ones, the aprotic solvents, they increase nucleophilicity by trapping the cation, the counter ion. For example, if you have sodium iodide, and here the nucleophile would be the I minus. The aprotic solvents, usually what they do is they trap the cation, counter ion, not the nucleophile. So by solvents that can trap the positive ion, make the iodide or the X minus, in this case nucleophile minus, make it available for the reaction. So the more the cation is trapped, the counter ion, the more nucleophilic it becomes. So the way this solvents stabilizes or solvates the cation is by ion dipole moment. For example, if you have acetone, it has a sigma plus, a sigma minus, which has ion dipole interaction that with sodium, for example. The negative ion, the sigma negative, would coordinate with sodium plus. That makes the iodine more free. So they free up the nucleophile. They free up the nucleophile. Makes it available for the reaction. So the more you use aprotic solvents, they enhance nucleophilicity by trapping the counter ion, the positive counter ion. It doesn't do anything in its presence, but deliver the nucleophile, obviously. So if you just have, say, any, for example, if you have sodium SH, so this sodium would be trapped by aprotic solvent, make the SH minus more nucleophile. The negative ion would be free, would not be so. But here's the opposite. The hydrogen bonding solubilize or solvate the negative ion. The negative ion obviously is a nucleophile. So the protic and aprotic solvents, they usually come and the students get confused about this concept. But make sure that one is making hydrogen bonding, which is a protic 1. By making hydrogen bonding with a nucleophile, it reduces the capability of the nucleophile towards that reaction. But opposite to this, the aprotic polar ones, would stabilize the cation. The cation is not involved in the nucleophilic substitution. Rather, they make, by bonding through ion-dipole interaction, they make the cation trapped, making the nucleophile more available towards a nucleophilic substitution. So this is an important concept. Any nucleophilic substitution reaction requires polar solvents in general, but some of the substitution mechanisms, we'll consider the mechanism also, would require a protic solvent. Some also need aprotic solvents. And make sure that you understand the difference between protic and aprotic solvent. Protic solvents are solvents that make hydrogen bonding possible with a nucleophile, hence they diminish the nucleophilicity. And the aprotic ones, they are polar solvents, but they trap the cation, the counter ion, to the nucleophile, making the nucleophile easily available for the reaction. So these are the main differences in terms of protic and aprotic solvents. So when you do exercises, make sure that, what kind of solvent is it? Acetone, acetonitrile, DMSO, THF, hexamethyl phosphoramide. These are all aprotic solvents. They don't have any hydrogen on them that can make hydrogen bonding. Here are aprotic solvents. These are like water, methanol, alcohol, ethanol, alcohol, tertbutanol, alcohol, and acetic acid. These are all protic solvents that would diminish nucleophilicity of a more solvated nucleophile. So we'll continue more on substitution. Let's study about detailed mechanisms of substitution reaction. So far we have just covered the nucleophilicity, basicity, alkyl halides, and also solvents. But in this section we'll be discussing more about the mechanism of the reaction. So this is what's really the core of a substitution reaction, understanding the mechanism of a reaction as SN1, SN2 mechanisms. All depends on the type of the substrate, meaning the alkyl halide, the type of solvents the reaction is being carried out. So focus on first understanding the mechanism of the reaction. So here you see you have a nucleophile, that's case 1. You have alkyl halide. So if the nucleophile comes in with a pair of electrons and attacks this carbon, obviously the leaving group has to leave. So that's the first mechanism, or one mechanism that's proposed in a substitution reaction. So what happens is a nucleophile comes, makes a attack on the carbon, the alkyl halide carbon, and obviously you don't violate octet rule, the alkyl halides leaves. So the resulting transition complex, during the reaction you form a transition state, which is the highest energy complex before products are formed. If you remember energy diagrams, that's what we call the transition complex. So the transition complex of this looks like the nucleophile start to make bond with the carbon, okay, and at the same time you have let me make this you have this complex, and at this point when the nucleophile comes in, the X starts to depart. So this is a transition complex, a high energy intermediate. As you see, the transition complex has highest energy, where the nucleophile and also the alkyl halides are involved in that transition complex. And finally, when it all leaves, it creates a new carbon nucleophile and this product. So this is a product, a substitution product. So this is one mechanism. Let me just also quickly go to another possibility how the substitution reaction can work. Based on the type of alkyl halide you have, the first thing that happens in the transition complex is the formation of this carbocation, meaning that what happens is, before this is formed and the nucleophile comes and attacks, the nucleophile is around here, but what happens in this mechanism we are proposing would be the carbon X bond, the carbon X bond becomes loose, meaning that hemolyze. That means the carbocation would be formed. So the carbocation is the only species that is present in the highest energy complex. So similar to this, before even the carbocation is formed, I will just make the transition complex. So the transition complex is where the hemolysis of X spontaneously, based on the type of solvent you use, this starts to happen. So you should have a good leaving group. When you put it in a solvent system, that starts to weaken. So that transition complex is what you see in one of the mechanisms. Then once you have that, the intermediate of that is a carbocation. Then the carbocation would be attacked by the nucleophile to form still the same kind of product, a nucleophile, to give this product. But here you see the way the reaction has gone through, or the way the reaction has materialized, is different based on the mechanism we proposed here. So in the transition state, in the case 1, both the nucleophile and the alkyl halides are implicated. Therefore, the first reaction type is called second order reaction. Second order. The rate kinetics for this is called second order. I'll show you why with the reaction equation. Here in the transition state, only the alkyl halide is implicated. The highest energy transition state is only the alkyl halide bond breaking. The rate determining step is the carbon X being dissociating. This is a first order reaction. First order. That is second order. Both the alkyl halide and the nucleophile are implicated in the high transition state. Therefore, in this second order reaction, the rate of the reaction is K times, rate constant times, the nucleophile and the Rx, the alkyl halide. That's why we call it a second order reaction, meaning that this reaction is first order with respect to the nucleophile and first order with the alkyl halide, 1, 1. So both would give you a second order. In this case, case 2, I'll just put A and B. In case 2, it's first order, and the rate constant is, the rate is actually not the rate constant, the rate is K times the concentration of just the alkyl halide. That's why the rate of this reaction is determined only by the concentration of the alkyl halide. Therefore, it is a first order reaction. It only depends with respect to the alkyl halide. So that's why we have another name now. Remember, this is an SN2 reaction. This is called SN2 reaction, and this one is called SN1 reaction, mechanism wise. So whenever somebody refers to SN2, you should remember the nucleophile comes attack at the same time when the alkyl halide is trying to dissociate. So that's why it's second order, meaning that both the nucleophile and the alkyl halide are important in the rate determining step in the reaction kinetics. That's why it's called SN2. So this SN2 means substitution, nucleophilic substitution of second order. So SN is called nucleophilic substitution of second order. What SN2 mean? And SN1 mean nucleophilic substitution of order 1, first order, SN1. So SN2 and SN1 are just because of all this mechanism. So they are important concepts. You need to understand this mechanism, these two distinct mechanisms. They require different mechanism. They are different mechanism. So later on we'll study also they require different kind of solvents, both. Actually, I can kind of mention now before, because we just mentioned about solvents. Usually the top mechanism is always taking place in solvents which are aprotic solvents. SN2 reaction is carried out in aprotic solvent, and SN1 reactions are carried out in protic solvents. The reason I'm bringing here is we just covered protic and aprotic solvent. So make sure that you understand this important concept in basic organic chemistry. So this is first order based on the mechanism. The mechanism involves first the hemolysis of carbon X bond, and then the nucleophile comes and attacks the intermediate. Here the intermediate and the intermediate consists both the nucleophile and also the alkyl halide. So in the next few slides I will also show you which kind of alkyl halides are undergoing SN2, which kind of alkyl halides would undergo SN1, because it all depends on the type of alkyl halide and the type of solvent you have. So in general now, make sure that for SN2 mechanism, you always have to have aprotic solvents, which I gave you in earlier section, and the protic solvents are good for SN1 reaction. So with this, I will continue discussing more with specific examples and energy diagrams of these two reaction mechanisms. So reaction mechanisms are very important. You need to review again this, and also the mechanism of the reaction also depends on what kind of solvents the reaction is being carried out. So in the textbook, for example, somebody would put here solvents. So solvents would be put here. So by just looking at the solvent, you can say, oh, this should be SN2. Oh, this should be SN1 reaction, because I have given you list of aprotic solvents and list of aprotic solvents, protic and aprotic solvents. So it's very easy once you understand how all these are derived and why. So this is a bimolecular reaction because this consists of both the alkyl halide and nucleophile. This is a unimolecular reaction because it only holds, or it's only determined by the concentration of the alkyl halide. Bimolecular, unimolecular. So second order, or a bimolecular. First order, it is uni-1 molecular reaction. SN1 is obviously you have 1, that's unimolecular, bi because you have SN2. So understand the mechanism, understand the arrow moving, which ways arrows are moving, and also remember the rate, the kinetic equations. These two equations are important as well. So based on the mechanism, you could have a bimolecular kinetics or a unimolecular kinetics. So we'll continue with more examples of SN1 and SN2. Let's continue with SN2 reaction. These are real life examples. For example, this is metal bromide. It's an alkyl halide. You have an acetate anion used as a nucleophile because you have O minus, even though it's not a very strong nucleophile. In the proper solvent, like acetone, you can form a substitution reaction between these two to form this product. So now I already gave you a hint that this is an SN2 reaction. So we'll work out all the details that involves this reaction. First, what would be the rate law for this SN2 reaction? Remember, SN2 reaction is a single step reaction where both the alkyl halide and also the nucleophile are involved. So if you're asked to write the rate law for this SN2 reaction, the rate law should be written as rate of the reaction equals K, any rate constant, times CH3Br, the concentration of the alkyl halide, times the concentration of the nucleophile, which is the acetate anion. So as it is indicated here, it is a bimolecular reaction because both are involved. That means this rate is a second order rate law, second order reaction. So this is metal bromide, which is your alkyl halide, and this is your nucleophile. So when we are investigating an SN2 mechanism, you'd be also asked draw the proper reaction mechanism using arrows. So what I'll do is, if you have CH3CO minus, that's the nucleophile, plus the alkyl bromide, your alkyl halide, the arrow movement would be, you have electrons obviously on this, the electrons would come and attack that carbon. At the same time, bromine leaves. So these are the arrows that you need always to write for SN2 mechanism. That means a nucleophile back attacks that carbon which contains the halide, and the halide dissociates. When the halide dissociates and a new bond is formed, you would have a product which is CH3O, which is a new bond, CH3 plus Br minus, a good leaving group. This is your leaving group. You should have a good leaving group for the reaction to happen as well. And this is your nucleophile. This is alkyl halide. That is the reaction mechanism with arrows. SN2 reaction. No matter what the alkyl halide is, no matter what the nucleophile is, the arrow movement is, a nucleophile comes, attacks that carbon which contains the alkyl, the halide, and the halide lives as a good living group. One other important thing is this is a single step. So reaction-wise, this mechanism is single step, meaning you don't form intermediate. Now, when we are studying the transition state and energy diagram, I'll be drawing the energy diagram as an example for this. So it is a single step reaction. So the energy diagram looks like, so this is the progress of the reaction in the x-axis of reaction, and this is energy. So in order for SN2 reaction as a single step, remember you should only have one curve, not two bumps in the reaction. So let's say your starting material, your nucleophile, and also your alkyl halide, CH3Br, and the nucleophile, which is O minus, are here to start with. So now the energy diagram looks like you have this, and this is a product. So if it is an exothermic reaction, that's what you'll see. But here I want to emphasize only you have only one high transition state without intermediate. So it is a single step, no intermediate. SN2 reaction does not have intermediate step. So I would say no intermediate. No intermediate. Remember also the solvent, I used a polar aprotic solvent. Acetone is, this solvent is also polar aprotic solvent. So remember, all these conditions are true for any SN2 reaction. That's why I'm giving you everything in one example. So it's a single step, no intermediate. But the transition state here looks like the BR is about to be broken, but the oxygen is about forming, and CH3. This is the transition state complex. Both the nucleophile and also the alkyl halides are in the highest rate determining step. So this step is from here up to there is activation energy. You need that much energy, activation, for the reaction to proceed. Okay? And here you see the final product, which is CH3. CH3 is the final product, lower energy product. So for SN2 reaction, it is just a single hump with no intermediate. Highest transition complex is important for two of the participants, the nucleophile and the alkyl halide. That's why you have this kind of rate kinetics. The rate kinetics is important. Of the nucleophile, that's why it's second order. SN2 reaction is by the nucleophile. That's why you have first total rate is dependent on both. No intermediate, single step reaction. When it comes to the energy diagrams, this is how you draw the energy diagram. You have your alkyl halide and you have your nucleophile at this energy. That's your starting material. It goes to the transition state. It is activated. When it's activated, the carbon-bromine bond is about to be broken, but the oxygen-carbon bond is about to be made. Now it collapses once everything is in place and the reaction leaves. You have the final product. So this is SN2 reaction in a nutshell. So SN2 reaction, as a review, is a bimolecular remember, it is a bimolecular reaction. Both are involved. And I'll reiterate again, this is an SN2 reaction. So similarly, I will also give you another example for SN1 reaction. Okay, so we just finished SN1 mechanism, SN2 mechanism, and now we'll be discussing on SN1 mechanism. So remember the alkyl halide we used for SN2 was, I didn't mention that, it's a primary alkyl halide because the carbon that contains the bromine only has one carbon. Actually, it's not primary. It will be the lowest level of metal bromide, which is very active toward this SN2 reaction. Here I want to characterize the nature of the alkyl halide. It is very important for this mechanism. So this is a tertiary alkyl halide. Very important concept for SN1 mechanism. This is tertiary alkyl halide. The type of alkyl halide also determines what kind of mechanism of substitution you can undergo. So first, this is a tertiary alkyl halide because the halide is on a carbon that is attached to 3 different carbons. So this is a tertiary carbon, and this is a tertiary alkyl halide. So I would just give you the rate kinetics or the rate law. Rate equals, in this case, K, rate constant, times just the concentration of the alkyl halide only. So this is a unimolecular reaction. So that means only the alkyl halides determine the rate determining step. So the slowest step, which usually we call rate determining step, RDS, is a unimolecular reaction. Unimolecular. Only one of the molecules is involved. That means only the alkyl halide is implicated in the lowest reaction state. So it's unimolecular. Usually it's undergone mostly in polar protic solvents. For example, you can run this reaction in ethanol, for example. Ethanol can be a solvent. Ethanol is a polar protic solvent. So remember, with SN2, I said acetone, which is polar but aprotic solvent. Here the mechanism would be, or the reaction would be facilitated under polar protic solvents. So now the next question would be, you would be asked to draw the reaction mechanism of this transformation. So if you know the mechanism, that's the first thing you remember. For all SN1 reaction, first the carbocation formation is the rate determining step. So in terms of drawing a reaction mechanism with arrows, CH3, C, CH3, CH3, Br, first step. So this is a unimolecular reaction, but stepwise it is two-step reaction. So don't confuse. It's a unimolecular species. That means at the rate determining step only the alkyl halide matters. That's why it's unimolecular. But in terms of how it proceeds, it's a two-step mechanism. So the first step, the bromine leaves. First step. That means it creates a carbocation. A carbocation is formed. So in the transition complex, when in the highest energy or in the rate determining step, so this is at the transition state. This is what you see, and finally this intermediate is formed. So this is intermediate. SN2 reaction doesn't have intermediate because it's a single step reaction. In a two-step reaction, you have an intermediate. Okay, next. Now this is the slow step in the reaction, slow step. But the next step, where the nucleophile comes and attacks that carbocation, is fast. So first step, second step is CH3 plus CH3, the nucleophile, which is this, which comes and attacks that carbon and forms the final product. Two-step. Step one is carbocation formation. That is a slow step, that's the rate determining step to form the carbocation. Once the carbocation is formed, that's why you have it only the alkyl halide is implicated. That's the rate determining step. Second step is the fast, that doesn't determine the rate of the reaction. So it is a two-step, but it is a unimolecular reaction. Remember, so don't confuse. Unimolecular because the rate is determined only by the alkyl halide. It is a two-step reaction, and the most important concept also is usually for SN1 reaction, your alkyl halide is better to be a tertiary alkyl halide. So in terms of SN1 reaction, usually methyl halide or just a primary halide is the best substrate for SN2. For SN1, you need always to have a tertiary alkyl halide. The reason being, the carbocation that would be formed is stable if it is a tertiary one. So actually the reaction is driven towards making the carbocation because the carbocation is stabilized by these metal groups or the carbons by inductive effect, stabilizing that carbocation. So SN1 reaction likes tertiary alkyl halide, primary alkyl halide or metal alkyl halides would undergo SN2 reaction. So these are also the distinction you need to remember. Solvent-wise, alcohols, acids are very good solvent systems for SN1 reaction because they would stabilize the nucleophile while the carbocation is being formed. So two very important details for any SN1 and SN2 reaction. So in the previous section I just told you about SN2, now this is SN1. How about the energy diagram for SN1? It is a little different from SN2. So if I have this progress of reaction and energy, first the rate determining step is the dissociation to form a carbocation. So that is the highest transition state complex to form a carbocation. A carbocation, which is this, is called intermediate. But here the transition complex is where it is almost hemolyzing. The bond is elongated and it's about to break. That is the formation of this is the intermediate, the transition state complex. Remember, there is a difference between transition state Okay, now once the intermediate is formed, the next step is the nucleophile comes and attacks. It needs a little bit of activation energy, but not much. Nucleophile attacked, the product is formed. So here, the final product is formed. Oxygen, CH3. This is the final product. Here the nucleophile comes, the nucleophile which is CH3 O dot 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 minus would attack that carbon. This is their activation, that's just formation of the new bond to form this. So here, but the rate determining step is this much activation energy. The highest activation energy is what matters for the rate. Here these are our starting materials, CH3, CH3, Br, CH3, and a nucleophile, CH3, O, acetate anion, nucleophile. So this is how the transition state looks like, very different from SN2. SN2 has only one bump, which is because it's a single step. This is a two-step or multi-step, two-step reaction. Two-step reaction, SN1, and it is a unimolecular. So it's a unimolecular SN1 reaction. Looks like this. Everything what you need to know as far as mechanism is concerned with arrows how SN1 mechanism looks like. So in the next section, we'll be discussing the implication of SN1 and SN2 reactions as far as stereochemistry is concerned, because there are changes in terms of stereochemistry from where the nucleophile comes and makes a bond. So next time we'll be discussing on the effect of all the substitution reaction on the stereochemistry of the initial alkyl halide.